So we will discuss improved WGAN, and this paper got quite a few citations, 10,000 citations just for doing a small improvement in the WGAN, and in almost all the GAN architectures, what we have seen is MLP based architecture. So the generator is some MLP and discriminator is also MLP, but in practice what is really useful is the CNN type architecture, because we are mostly working with images, generating images and things like that. Okay, there is also some amount of engineering involved if we use GAN like architecture. So that's how you get into ideas like progressive GAN for super resolution, okay, or you can go into style GAN. So all this uses a lot of engineering, which I will cover in the next class. So we will do GAN engineering. Okay, we will build some very nice architectures for GAN that will do interesting problems. Okay, but today we will try to kind of get into CNN as a last step. So we will, some of you might know CNN already. So we will discuss CNN and conclude, and then next class we will see all the various types of GAN and what things people are doing. Okay, so for today let us focus on this. So as I said, the first part is can be starred, so you can skip that. This is a little bit of the advanced analysis, but some of the things, if you can just take assume, then it's okay. Okay, so the proof will be still okay to follow, but just for completeness I'm going to describe few things. So there is an area in analysis, it's called topology, and that's like a higher, like a bigger space where the matrix space lies inside some topological space. Okay, so what mathematicians usually do is they try to kind of see in how general things can be. Okay, so in topology basically you don't even have the concept of a metric. Okay, you only work with open spaces. Based on open sets only, you decide whether the function is continuous or not, which looks very strange. Without a metric, how can you say function is continuous or not? But that's how it is. So some of the things like compactness and all this is defined there, but I would say we can always go back to a spatial case like Rn and metric space. So anything that I say here actually holds for Rn, because in Rn we know what are open sets anyway. So although it looks a bit general, but we can make it a spatial case for Rn. Okay, so topological space will be a set X and a collection of subsets of the set X. So and this space, we call this topology if the empty set and the whole set are in this collection, and any union of members of this tau is also in tau. So you take any, because you have already came up with tau, a collection of subsets of X, and then you have to satisfy that any union of the members of tau is also in tau. Okay, and any intersection of finitely many sets, members of tau are actually subsets of X. So if you do intersection, then it's also in tau. Okay, so that's like a general. It's called topological space now. So so as such, as you can see, although these things are studied in advanced maths, but as such the definition is very simple. So you can think of any set X and a collection of subset of X. Obviously in the collection you should have empty set and the whole set itself, and your collection should be such that if I take any arbitrary two sets from the tau, if I intersect, then it is in the tau. If I take a union, it's in the tau. Okay, so that's basically, so you can play around with some simple example. So as a very simple example, maybe let us say X is our set A, B, C, and then I have to specify tau. In tau certainly I must have phi and the whole X, but then I'm supposed to put some X, some subset of this guy. So it could be maybe this or this, and maybe I guess this works. Okay, so what I have done is that I'm given a set X which contains A, B, C. So the empty set phi is there, whole set X I have put there. Now the second and third thing I have to check is any union of member of tau is in tau. So, okay, so let me take a union. A union B is in tau. Yes, A, B is there. A intersection, or you can do any other union also. B union AB is there. Phi union X is phi union A is A, so it's there. X union A is whole X, which is there. If I look at the intersections, then A intersection B is phi, which is there. A intersection AB is A, which is there. A intersection A B intersected with B is B, which is there. Okay, so this collection is valid. Okay, so then I can say that X tau is a topological space. Okay, so if you have doubt, you can always stop me. So as you can see, earlier we said a set is open, a set S is open if all interior of S is the S itself. Okay, this is what we defined in the metric space, where we said if I take any point from S, and if I can always find a ball such that the whole ball is inside S, then those points are interior. And if it happens for any point on S, then we say the set is open. Okay. Now, if you can see, the open set is now generalized here. Now, what we are saying is that the elements of tau that you have collected here, it looks abstract, but we declare them as open sets. Okay. So in a bigger topological space, so topological space is somewhere here, metric space is here. Okay, and then you can build few other spaces around this, but topological space is more or less the highest level. Okay. So this is a very like general way to say how to define an open set. So if you want to work with R and see how things look like, then consider the set of all real numbers where the open sets are defined as union of open intervals. So open sets in R are like open interval. Then this forms a topology as well. Okay, so you take a collection of all open intervals of R. So R combined with the tau, which is collection of all open intervals, forms a topology. Okay. Similarly, you can think of a discrete topology in R, where every subset of R is will be considered an open set. So this will also include like singletons and things like that. So and then the trivial ones are like empty set and the whole set. So and then to define a compact set in a very broad way, so let X be a topological space and A be a subset of X, then an open cover of A, so we are looking for a cover, so I'm defining that. So an open cover of A is a collection of open sets in X such that that if I take the union of these OI, which are the open sets, it covers basically A is subset of that. So then we say that this collection of OI are a cover of the set A. Okay, so this is also very easy. It's just that they have to be kind of open sets. Okay, it's a collection of open sets. So given any set A, if I can have open sets which I can take a union of, and then it covers all the sets, so that the set A is subset, it's called an open cover. So then we can define a compact set. A compact set is a set if every open cover has a finite subcover. Okay, so here I can replace this by topological space as well. Okay, so every open cover, if it has a finite subcover, so what does that mean? So it may happen that sometimes the cover I need infinitely many of the open sets to cover a given set. Okay, so it may happen that the collection OI that I need are like infinitely many of them, but what it says is that for any open cover, if you can find a finite subcover of that, okay, or you can write the union as a finitely many of the OIs, then we call then it's a finite subcover. Okay, so if you can do that, then we call that set a compact set. Okay, so this is a definition of a compact set, and if I have to make it specific for Rn, which we usually deal with, then in Rn every closed set we know. Okay, so closed and bounded set is compact. Okay, so to be very specific, the definitions are very general, but in Rn, closed and bounded set. Okay, so let's say in R, closed interval is a compact set. Why do we study compact set? Compact sets are sets where the functions are guaranteed to achieve extrema. Okay, so they can achieve the extremum value. So these are examples of a compact set. Closed and bounded, as I said, in R will be a compact set, and then in case of finite sets, these are the examples that you can have a look later. Okay, so what is interesting for us is the extreme value theorem, which says that if you have a continuous function on a compact set, the domain of the function is compact, then indeed that function attains its maximum minimum. Okay, so that's the result that we want to use. Okay, even if you kind of ignore other things, but what we really want is there a guarantee that I will get extreme values, the minimum and the maximum? So the analysis says that yes, if you have compact set, then the minimum and maximum is guaranteed. So you can have a look into these examples. These are easy examples to work out. I will skip that. And Lipschitz continuity we have already seen, a function is Lipschitz continuous if the mod of fx minus fy is less than or equal to norm of x minus y. I have already used this in KR duality. And one of the things that we may want to see is, does there exist a function for which equality is achieved, right? So let us say Lipschitz continuous means like set of functions, one Lipschitz functions, right? And there are many f, okay, that satisfy this. But in that space, can I define an f for which the equality will be achieved? Okay, so then these things are guaranteed when you have compactness and so on. Okay, so we are prepared to now look into this improved WGAN. So this is taken from the WGAN paper. You can refer to that. So what this says is, so in WGAN, obviously, like we are working with marginals, real distribution, and then the generated one. So let PR, let's say P real, and PG with the PDF of real and the generated one, and we have a compact space, and this is something we are going to use later on. Then there is a one Lipschitz function f star, which is the optimal solution of this. So remember, this is something we saw in the last class, right? In WGAN somehow stops here, right? So WGAN is basically supremum of, maybe we have used h there in the last class, h of y minus expectation of h of x, right? But here they change it to f, okay? And these are one Lipschitz functions. So this notation says that fl less than or equal to 1 is kind of one Lipschitz, right? So what this result says is that, so let pi be the optimal coupling. In other words, like there exists a joint distribution for which the infimum is achieved for the Wasserstein, because Wasserstein, the original definition is like it's infimum over the all possible joint distribution, right? So let us say that there exists such pi for which optimal is achieved. Existence we are not going to prove, and okay, so we will just assume because of the compactness and so on. So but what is important from practical point of view, algorithmic point of view, is this result. So it says that there exists a one Lipschitz function f star, which is a solution of this. So from KR duality, what we know is that that W is equal to supremum of this. So what this result says is that there exists an f star for which this happens. Moreover, you also have this. So what this result is saying is that the gradient of that f star is 1. Okay, the gradient of that f star, although it's written in terms of like probability of and so on, but essentially what this result says is that there will exist an f star which will attain the supremum, but you also have that gradient of f will be 1 at some xt. Some xt exists. Okay, some xt exists for which the gradient is 1. So as an algorithm guy, what you do usually is that you saw the WGAN, okay, and you know WGAN is filled in like optimal transport books and things like that. So what they did, they went into these KR duality results in the Cedric Villani's book, and then there they found these results which they simply used. So what was useful from as an algorithm guy is this result, that it's not just about having f star which satisfies this, but I also get this as a byproduct. Okay, so why not use this in the algorithm, right? So when you see results like this, then you say, okay, I also have additional information that grad f star must be 1. Okay, so why not use this as an additional constraint in the optimization, that not just minimize this over f, but also the gradient of f should be equal to 1. Okay, so it's like optimization problem, but also additionally you are giving more information to the optimizer that this is an additional property that you should include, and that's why you get improved WGAN. So we will try to prove this result. Okay, the result itself is not simple. Algebra is needed. So we will go step by step, so don't get overwhelmed by all this. So let us start with the existence proof, which we take it from optimal transport book, let's say. Okay, so there will be the f star will exist, okay, for which the one Lipschitz will be equality. Okay, so it says that it's a supremum over over all one Lipschitz function. So basically it's like less than equal to, but what we are assuming here that there will be one of the f star for which it becomes even equal. Okay, so that's like so as an algorithm guy, sometimes you scan the books and then see, okay, which results I can use. So this is one of the results you can pick from the book. Okay, and then the remaining part that we have to prove is that the gradient of this guy must be 1. Okay, so that will follow. So let us see. So let us say there we have xy and then f star y minus f star x is equal to norm of y minus x. We can safely assume that x not equal to y. So so that's like all given from the existence result, and we can construct as xi t, which is f star xt minus f star x. So xt, if you recall, was this guy, right? xt is 1 minus tx plus dy. Okay, so this is what we are going to use it. So at t equals to 0, it's at the point x. So it's the convex combination, right? Convex combination of x and y. So t equals to 0, it's at x. T equals to 1, it's at y. So these are the things we keep in mind, that psi t, which is f star xt minus f star x, and then as a first step, what we prove is that psi t is t of norm y minus x. Okay. So so let us try to prove that psi t is t norm y minus x. So this is the claim we are now trying to prove. So here, if we see here, so psi t is norm t of y norm of y minus x. So let us take obviously. So let us take t prime in 0, 1. Then let us look into this where we have psi t minus psi t prime. So psi t will be f star xt by definition, right? So psi t is f star xt minus minus f star x, right? And then psi t prime. So basically f star x will get cancelled in, because psi t prime will also have f star xt, but it will become positive because of the negative here, and psi t also has this f star x. So you will be left with f star xt minus f star xt prime. Okay, so all of you get this, right? So this is up until here it's fine. So now f star being Lipschitz, right? So the f star being Lipschitz, then it is less than equal to xt minus xt prime. Okay, so so then in so when we look into xt minus xt prime, then xt was, so basically we have to do a bit of calculation here, I guess. So what was xt? Xt was 1 minus t, right? So xt was 1 minus t x plus t y minus, and let us put this in this. So and this is 1 minus t prime x plus t prime y. Okay, so this is our xt, and this is our xt prime. So if we do this, then after simplification, so what we get is, so this is all under the norm. So under the norm, then what I see is that x goes away, and all this. So eventually what we should get is y minus y. So I can see this, so y minus 1 y is there. Okay, so t minus t prime I can see here. So 1 t minus t prime is with the y, and 1 t minus t prime is with y, and another t prime minus t is with x, it seems. So t minus t prime, let me write down, t minus t prime, I can see this with y, and plus t prime plus t prime minus t is with x. X goes away. So since x goes away, I can cancel out this guy, and that's all, I guess. That's all is remaining. So here we have plus, right? So we can change this a little bit. So this is like y minus x we want to do, and this will also help because we want to take t minus t prime common. So t minus t prime common, and everywhere it's norm, and so this is t minus t prime common, and then this is y minus x. So obviously t minus t prime being scalar, so mod of t minus t prime will come out, and what we have is y minus x. Okay, so this is the proof we did. So this part is okay. We have proved this. So therefore, psi is x minus y Lipschitz. So you get that, right? Because you see, psi of t minus psi t prime became norm of x minus y times t minus t prime. So that's the definition of Lipschitz continuity, right? So Lipschitz continuity is like fx minus fy is less than equal to norm of x minus y and some constant here. In our case, it so happens that now norm of x minus y is behaving like the constant that we are looking for. So another way to write this would have been put the guy that is independent of t as in front, and then you have this t minus t prime. Okay, so this is less than equal to some L times t minus t prime. So this proves that that psi is this L, we call this x minus y ellipsis. So we call this like x minus y ellipsis, right? So we have this this first half. So therefore psi is x minus y this ellipsis. That's fine. Then let us look into psi 1 minus psi 0, right? So let us look into psi 1 minus psi 0. So let me just clean this part. Okay, so let us look into now psi 1 minus psi 0, right? So psi 1 minus psi 0 is we can see this as we can introduce psi t here artificially. So I just added one psi t term there. So add and subtract psi t. Then what does it give? So psi 1 minus psi t I know, right? Because in general I know what is psi t minus psi t prime, right? So then I can use that result to write what is psi 1 minus psi. Yeah, so from here psi 1 minus psi t will be what? So basically t is our 1 and t prime is our t, right? So from here what do I get? From here I get basically t minus t prime. So in this case 1 minus t and then norm of x minus y, because psi was x minus norm x minus y ellipsis. So we have that anyway. And now we look into psi t minus psi 0. So now our t is t and t prime is 0. So then so here I didn't do anything yet. I just keep it like that. We will see this, I guess, in the next one. So here again, anyway, I did that, right? So anyway, I use that result here. So this is like t minus 0 times norm x minus y. So this is also okay. So overall, these guys gets cancelled. The t part. So only the 1 times norm x minus y remains. So psi 1 minus psi 0 is norm of x minus y. So okay, so now let us so what we were trying to prove, right? So let us keep track of what we are trying to prove is we claim that psi t is t norm x minus y. We are still here, right? So we are trying to prove that psi t is t times norm x minus y. So this is where we are going. So however, psi 1 minus psi 0, if we put then basically so psi 1 will be at 1, right? So at t equals to 1, what do I get? At t equals to 1, so basically xt was 1 minus tx plus ty. This also we keep in mind, right? So for t equals to 1, I get y, so which is like f star y, and at 0 I get f star x. Okay, so for t equals to 1, I get into f star y, and then in this case, and then but then I know that f star is such that it's equal to norm y minus x. Okay, so this is coming from the existence result, so that we already know. Okay, so psi 1 minus psi 0. This is what our definition was, right? So psi 1 minus psi 0 is basically, it means f star x1 minus f star x, and then f star x0 minus f star. So f star x get cancelled, right? That's what we did here, right? So psi 1 minus psi 0 from our previous definition is psi 1 minus psi 0. Yeah, so the other way, psi 1 minus psi 0 is from here using this fact. So this is like f star x1 minus f star x minus f star 0 x0 minus f star plus f star x. So this guy gets cancelled. So basically we have f star x1 minus f star x0. This is what I used. So f star x1. So f star x1 is just y here, and f star 0 is just x here. And for that I know that it's norm x minus y. So the inequalities have to be equalities, or in particular psi t minus psi 0 must be t norm x minus y, this inequality. And here we are comparing these two guys. Okay, so we are saying that these two terms are equal. then these have to be equal, because we have independently proved that psi 1 minus psi 0. We have independently proved that psi 1 minus psi 0 is indeed norm x minus y or y minus x, it doesn't matter. So we have independently proved that that psi 1 is indeed equal to norm of x minus y. We have independently proved. So wherever there was inequality here, is supposed to be equality now. And in particular, this is something we can use. So we can say that psi t minus psi 0 must have been equal to this, because the first term are already equal. So we can claim psi t minus psi 0 is t norm x minus y. So that's what we say. Psi t minus psi 0 is equal to now t norm x minus y, and psi 0 is 0. Why is psi 0 0? Yeah, so psi 0 is, in our notation, psi 0 is f star of x0. Oh, that gets cancelled actually. F star of x0 is x. Okay, that was trivial. So f star psi 0, so yeah, so f star x0, right, minus f star x. So that's how the psi 0 was defined. But f star x0 was f star x only, right? By definition, it gets cancelled, right? So psi 0 is indeed 0. So so then from these two guys, we can immediately claim that psi t is t. Psi 0 is 0 anyway. So psi t is t norm x minus y. So we prove this. Now we look into so this v, the vector, was kind of there in the here, right? So this is the guy v that we choose here, and we want to see so how so basically we will compute a directional derivative in this direction of v. Okay, but I will come to that. But let us start with v first. So v is, what was v? V was y minus xt divided by norm of y minus xt, and we simplified. So this is easy steps. You can check. This is nothing but, and so v is like y minus x divided by norm y minus x. Okay, things get cancelled out and so on. And this guy is positive, and this guy is also positive, so you can also cancel out this. So this is okay. Now we look into f star xt minus f star x. So what we know is that this is equal to psi t, which eventually is equal to t norm x minus y. So from there, what we can write is f star xt is equal to, so basically we move this f star xt on the right, then we have f star xt plus t norm x minus y. So until here it's fine, I guess. And then what we do is we take a directional derivative of f star in the direction of v. Okay, so if you recall the directional derivative, right? Because if you are working with one variable functions, then derivative is like basically your along the let's say x-axis, right? So there you don't have like trouble with directions. But if the function is multivariable, then you have to first tell in which direction you want to see. So there is axis, but then there are infinitely many directions, right? So in this case, we are saying let us calculate the change of the rate of change of the function along v. Okay, so basically that we call directional derivative. So this is the definition of directional derivative. So this is f star xt plus hv minus f star xt divided by h, and limit h tends to 0. So this is the directional derivative of f star along v. Okay, and this is equal to I guess we have substituted v. Okay, and the last term remains the same. So what happened here is h and v is, yeah, even xt is expanded. So if you see, this guy is xt. So if you write it in it is exactly in this form, right? So you can write this as 1 minus tx plus ty. So I've just written it slightly differently. So this is xt that we recall, and the remaining part, hv part is this guy. So that is also quite clear, right? So this is hv, because v was y minus x divided by norm y minus x. So there is this v here, y minus x divided by norm y minus x. And this f star xt is anyway already there. Now what we do as a next step is that we want to see this change in x. So we want to kind of like see this. So this is like x plus something, right? X plus something y minus x, right? So this guy from here to here, if you can see, is like that, right? In fact, this is xt is also seen like that, right? So xt here, in fact, this is what we wrote it here as well, right? So this is like x plus t y minus x, right? So it's like I start from x and then I go in the direction of y minus x, right? With t magnitude, right? So this is another view. So what we want to see this this guy now, this guy here, this is of the form x plus, as I said, something y minus x. That something is the t I'm looking for. Okay, so it's like so this is what we write it here. So this x plus t plus h by norm y minus x times y minus x is nothing but, it could be seen as x t plus h by norm y minus x. Okay, so yeah, I mean, you just take y common. It's very simple to prove. So let us do it very quickly. It's right there. So it is right there. So this guy, this is f star, and then we have x plus t plus h by norm y minus x, and then y minus x. Okay, so this guy is like that. So this guy is written like that. So I've taken y minus x common, and whatever remains is like the t that I'm looking for. So this is like t plus h by norm y minus x. So this is being used here, obviously. So I could rewrite this in compact form. So this is f star x t plus h by norm y minus x minus f star x t, right? Okay, so then let us clean up a little bit. Okay, so now let us look into these steps. Okay, what did we do here? Right, so we are using this guy here, and we are using this guy here as well. So in place of xt, you can think of x t plus h by norm y minus x. Then it will be f star x, which is already here, and in place of t, you have t plus h by norm y minus x, and then norm y minus x is already there. So that goes for the first part, and for the second part, it's just the f star xt. So that's exactly the same thing that I am supposed to put here for the second part. So all right, so from here we have all this sorted. Now it's about taking the limit with respect to h. Remember, there is always a limit outside. So let us see what happens. So there seems to be quite a few cancellations here going on. So the first thing I see getting cancelled is like f star xt surely, and t norm x minus y is getting cancelled already. So you can see t norm x minus y, this guy is getting cancelled. Yeah, it's getting cancelled because of minus is there, right? So what you're left with is basically h norm x minus y divided by norm y minus x, and h also was there in the denominator. X minus y, y minus x is the same thing. So eventually you're left with h divided by h, which is 1. Okay. So what we have shown is that the directional derivative of f along the direction v is 1. Okay. But this doesn't show that the gradient is, the norm of the gradient, the original definition was, so what you have seen shown is a special case, right? So here if we have a multidimensional function, so in this case let us say f of xy, then we know that the gradient of fxy is del f del x del f del y. So this is like it's telling me what is the variation along the axis. Okay, and then I can use them. So I can obviously it might be varying more along the x-axis than the y-axis, right? So depending on how these variations are, it will tell me which direction the function is increasing a lot more, right? So this itself is a vector. So it could be like this. It will say that your function, if you go in this direction in your domain, then your function has the steepest increase. So this is the gradient. Now directional derivative, I can say any arbitrary vector. So I can say this is my vector v. Tell me what is the gradient of the function in this direction specifically. Okay. So this is directional derivative. So what we have shown is for one direction v, the gradient is 1, right? Along that, but then we want to lift it to the gradient and conclude that the gradients direction how it will be, because the original theorem was with the gradient. So we need that last part which is here. If it so happens that fx minus fy is less than or equal to norm x minus y. This is one ellipsis, so I put a 1 here. Then prove that the gradient, norm of the gradient, is also bounded by 1. Okay. So this is a classical result. You may just start with definition and kind of prove this. So this is more or less there because f star was already one ellipsis, so the gradient will be bounded by that constant. Therefore, by simple Pythagoras theorem and using the fact that v is a unit vector, v is obviously a unit vector because norm of v will be like norm of y minus x, and below there is already so norm of v is indeed 1. It's a unit vector obviously. So we start with this fact. So 1 is less than or equal to gradient of f star xt. So the first one is okay. That's the ellipsis continuity. So what remains to show is that these are indeed orthogonal components. So what we have done here is that we have projected v, or rather we have projected gradient, which is a vector in itself. So we have projected the gradient. By projection we mean just take inner product. Okay. So then we have this component where so this is the one of the component after projection, and then we have another component in the orthogonal direction. So this is our v, and this is our v perpendicular. So this is what is happening here. So along v we have some projected component which is inner product of grad f star v. That's the first term, and the other one is after projection through the orthogonal direction. Okay. So as an exercise, again, prove that these are like orthogonal directions. Okay. So if that is the case, then if two vectors are orthogonal, okay, then if we have norm of x plus y, then we can write if x and y are orthogonal, then we can also write like this. You agree with that? So a norm of x plus y is like if you are familiar with let's say the dot product, and then x plus y transpose x plus y. This is norm of x plus y whole square. So this is x transpose x plus y transpose y plus 2 times x transpose y, but x transpose y goes to 0 because x is perpendicular to y. So indeed this guy is norm x square plus norm y square. So this is Pythagoras theorem. So norm x plus y whole square is norm x square plus norm y square. So that's being used here. And the first term that you see here is nothing but the directional derivative, because directional derivative are like that. They are seen as projection of a gradient on the direction that we are looking for. Okay. So in case you don't know, you also see this as a definition. Okay. This is the previous one. The limit definition of directional derivative is this one, and if you have a gradient in hand, then you can simply project the gradient on the direction that you are looking for. So if this is the v, then you just take a projection, and that is exactly the directional derivative. So whatever gradient component you have after projection, you will get that gradient component along the v. That is exactly what directional derivative means, right? So So this first part is indeed the directional derivative that we have already calculated previously. So this is nothing but del by del v, which is the notation for directional derivative, f star xt, and then the remaining this guy also is a directional derivative again. So we have substituted it there. Okay. So what we have is this, and then we wrote this in terms of directional derivative, and we have shown previously is directional derivative is 1. So this guy is 1, and the remaining one grad star fxt grad f star xt is there already, and this is also 1. So that 1 is used already, and what is remaining is v. So v is kept there. So this is clearly greater than or equal to 1, because on here you have the norm guy, right? So norm is always greater than or equal to 0. So overall this 1 plus something greater than or equal to 0 is now greater than or equal to 1. So what we proved is that 1 is greater than or equal to 1, but we know 1 is equal to 1. Same trick, inequalities become equality and so on. So hence you can say that the inequality that you saw from here, you can say they are equality. So let us say that they are equal. So 1 must be equal to 1 plus grad f star xt minus v. So 1 gets cancelled. So we have this guy here, and from there we have that grad star f xt is v. Okay, because norm of x minus y equal to 0 only happens when x is equal to y, right? So that's the distance property that we use. And we already knew that v is indeed y minus xt. We already knew that. So y minus xt by y minus xt, right? So so to conclude, we saw that if xy has a property that this happens, then indeed grad f star xt, which could be any arbitrary between x and t, indeed it becomes grad f xt indeed becomes 1. Okay, in particular grad f becomes y minus xt divided by norm y minus xt. But if we take the norm of this guy, then so what this really implies is the norm of grad f star xt becomes 1. So improved WGAN, what they said is that why not use this fact? Okay, you also have the additional result that grad f star x will be equal to 1. Okay, so that's what they did. They use a gradient penalty here. So this is until here it's WGAN, but here if you see, this is the famous gradient penalty, or sometimes they call it WGAN GP. Okay, so this stands for, so here you can clearly see this is the gradient of the d, which originally in our notation was f. So here originally we had f, but now in the GAN notation f was the discriminator. So what it says now is that the gradient of the discriminator, which you have access. So PyTorch will calculate these gradients for you anyway. So you enforce this as additional constraint. Now how it's written, this is a penalty form, right? So if some of you are not, so what actually we had to do was like this, right? Supremum of expectation of d x minus expectation of d x, where this is x is like generated and x is like real, or in our notation I think this was real. Yeah, so it was like this, and so this is an optimization problem where we want to maximize this. And additionally what we said is that grad of the discriminator in our case is 1, right? Such that, right? So our original problem is like this: minimize the so essentially this is Wasserstein. So minimize the Wasserstein, meaning this guy, such that the gradient norm of the gradient is 1. So what we did is that we wrote this in penalty form. So we said that rather than taking this as a constraint problem, why not introduce a penalty form? So this is like one way. So how penalty form works is like, let us say you have an optimization problem like that: minimize fx such that hx is c or something like that, right? So penalty form says that change your objective to to like this, lambda of hx minus c. So will it work, right? Original problem is to solve, minimize fx and satisfy an equality constraint, and the penalty form says like we can do like this. Yeah, it will work if lambda is very large. Then what you are telling the optimizer is that force this guy to be 0 as well. Okay, so if lambda is large, optimizer is supposed to minimize, right? So optimizer is supposed to minimize fx, but additionally if lambda is large enough, again lambda is a hyperparameter. Okay, so you will play with this. So how large, because if it's very large then it may forget fx perhaps, okay, and just minimize this because it sees benefit in just minimizing the last one because of the lambda being very high. Just minimizing that minimizes the cost drastically. So one has to play around a bit because your original objective was to also minimize f. So there lambda is a bit of a hyperparameter here, but let us assume lambda is like large enough, and then so what it does is that apart from minimizing fx, it's also trying to minimize hx minus c. So basically it's trying to force that hx is equal to c. So this we call it penalty form, right? So that's what they did. They don't want to solve a constraint optimization problem. So we have seen some idea about constraint optimization problem. We form a duality Lagrangian dual, but that becomes a bit cumbersome, right? So this is another way to solve where you write this in a penalty form. So that's what they did. They had to satisfy the gradient of the discriminator to be 1. They just put it there. So in PyTorch, all these gradients are accessible to you at the current iterate, obviously, at the current weights, and you keep enforcing this. So you will say, I don't just want d with the weights like that, I also want the gradient to be 1. And that will nudge the optimizer to converge faster into better optimality, because as such these problems are not necessarily convex. So giving additional information about the gradient perhaps helps it to go and find a optimal f, okay, or in our case the d that we have. Okay, so yes, any question? Yeah, but yeah, that is the f we are trying to get there, right? So our discriminator is also learning, right? Discriminator comes with some initial random weights. It keeps getting updated. The weights of the discriminator keep getting updated. So this is going towards f star. We are trying to help go towards f star. This is not yet f star, but what we are saying is that whatever it could be, it must be the one which gradient is 1, norm of the gradient. So basically we are helping. Okay, it won't get there in one shot, but this helps because this helps only searching for those for which gradients are 1. So it's kind of narrowing down the search, which helps in this case. Okay, so yeah, so f star, f in general there, in our case it's f. Obviously this f is like iterative, so it's you can say it's like some t there. It's improving each time the discriminator weights keep getting updated and so on. So more or less this is what improved WGAN is, and more or less everything remains the same like what we had in the they are doing some kind of interpolation also here. So sometimes few things are like that. So other things are like Adam. Yeah, Adam is the usual optimizer. In place of SGD you can use Adam. Your generator is G theta. Z is the noise random. In this case they are taking uniform. Yeah, more or less everything else is similar. Lambda they choose is 10. So somehow it works for them. So the penalty term, the constant lambda is 10. The loop for the discriminator n critic, this is the for loop, and that is running 5 times. So 5 times discriminator is getting updated. So W is the weights of the discriminator, and then once the generator weights are getting updated. Okay, the generator has to do descent. So we see this minus here, minus of the gradient here, and this guy has to do ascent here. Okay, so L is this whole loss. So yeah, this is pretty much improved WGAN. Somehow it works pretty well, and this more or less is used in the current form. You may try to implement this. So these are the images generated by WGAN. Obviously, you may not be able to see this. I have some zoomed in pictures as well. So this is a bedroom data set, Elsun bedroom data set. So your samples are various bedroom designs, pictures, and then it generated some of its own design here. So maybe in the paper you can go and zoom in and see. I think I have one slide on that here. So they also compared with some other variants of GAN. As I said, there were many variants of GAN proposed just after Goodfellow GAN. They proposed in 2014, and then there were a couple of variants for that. So this seems to be there, WGAN GP they call it, and they use some architecture, they call it ResNet. So if we have time, we will see that a bit later. And these are yeah, some other type of GAN. And what they are showing here is a score, right? So when you are generating images, then one of the things is like, how do I know that generated images are good? Like, how do you judge the quality of generated images, right? This itself is actually it's a kind of an open problem. It's not easy to say. An image that looks good to you may not look good to me. So sometimes we have a bias also, right? So this itself is a tricky thing. But for one of the data set like CFAR 10, someone has worked out a score which is called inception score. So there are like 10 types of objects, and so in this data set. And then usually when you work on generative modeling, you have the CFAR 10 data sets, and then you compute this. So after generating the images, you pass this to the inception score calculator, and it calculates and somehow gives you some quality of the images that you generated. So this is quite standard. People use this. So higher is better. You can go up to 10. So what they did was their score was like 7.86. So this seems to be kind of the best. But I mean here, but they also claimed in the paper that there was another GAN, which is SGAN. They were the best actually. So this is not, so this is there. So they also did some conditioning that we will try to see a bit later. There is a slight change they did, and then they reported 8.42 as well. So overall, this was the status, I guess, 2017. So many things have evolved. So we will look into the various interesting GAN in the next class. But today we are looking at in machine learning. 2017 is considered old. Okay, 5 years. So these are the zoomed in generated images from WGAN. Some of the things that you see look quite okay. This is a design of a bedroom which looks kind of interesting. But sometimes if you see, this gets messy, right? You can hardly identify a complete bed or something, like it's completely mixed up. So these were some initial results. These are not easy tasks to design and think about new bedroom design and things like that. But these were the initial results which were kind of state of the art in 2017. And things have improved drastically. So you will be amazed at what GANs can do now. So we will see that in the next class. This is the standard CFAR 10 that I told you. This is typical data set that people use. It's a very small resolution. That's why it looks pixelated. So here they tried. And as you can see, you can find some troubles, right? So here it may be airplane or bird, I don't know. So here it's kind of tries to figure out the features of a car. Here it's looking a bit confused. At least I'm confused, like what kind of animal it is. So these were the early results, and yeah, not maybe perfect, but yeah, in those days these were considered quite good. So so what actually is used in the GAN type architecture are something called convolution neural network. So it's called CNN. So what we have seen in the code, in the Python code, was a usual MLP, okay, multi-layer perceptron. But for images, it turns out that you should rather use, because GANs are used mostly for images, so you should rather use CNN type architecture. So that will be my second part of the talk, where I will introduce CNN. Some of you might know this already. but it may be a good revision as well. So this is the overall architecture of a GAN type network. You have a generator here, you have a discriminator here. So generator takes in the noisy images, okay, so which are like standard normal or uniform distributions, and then basically it goes into yeah, so it generates some sample basically. Initially it will be very bad, not as good as it's shown here. So initially it will be very bad. It will go to the discriminator. A discriminator will say, yeah, this image doesn't look. It's discriminator will try to like learn the score on that. So for the real one, the level is already known. So when you pass the real one, the discriminator is told that it is real. Okay, so I can say 1. Yeah, it is like real score is 1. So I already tell you that this is good one. So discriminator is also learning in the process. So when it sees the real one, it's updating the weight also to learn how to classify real samples. And initially the fake ones are coming, and then it is given the fake label as well. So overall, what is happening is the discriminator, as such, learns to classify the real images, and but gradually the generator, because each time initially the generator will produce an image, it will be kind of bad, and discriminator will say, no, it's bad. So what will happen is the generator has its loss function, right? So when this discriminator flags that what you are generating is a garbage, then the generator goes and updates its weights, okay? And so updated weights, and next time again some noise vector comes in, again it produces a garbage, and again generator says, no, what you are producing is really bad, and so on. But in the process, generator keeps learning, and what happens is that generator learns so well that there comes a time where even discriminator gets confused. So discriminator at some point, it is supposed to produce a score between 0 and 1, but at some point if it starts producing somewhere around half or something, let's say, then you know that for generated images, if it starts producing, it's getting confused, then you know that, okay, generator seems to have learned, because even the discriminator is not able to tell whether it was real or fake. So this is more or less the architecture. This is what we will see sometimes when we go into from maths to engineering, then we go into these architecture level details, which we will see quite a lot in the next class. So what we will see is this convolution architecture. Okay. Yeah. So let us start with CNN basics. Slides are taken from CMU as usual, deep learning course. Let us say we consider the recording of a speech. Okay. So we can think of these as spectrogram representation, essentially kind of 1D. So the color intensity at any pixel will denote the spectral value in this case. So does this signal contain the word welcome, right? So we can have a speech recording, and then what we want to know is whether there was welcome word somewhere in the recording. So we can pass this through MLP also, right? But what is the problem, right? To process the word welcome in audio speech, what is the issue if I use MLP, right? What do you think is the problem? The network that finds welcome word in the top recording, let's say it's here, we may not be able to find this in the lower one, unless this was also part of the input sample training data, right? So the problem here is what? Problem here is that although the word welcome is somewhere in the data, but it's not necessarily at one location, right? So to detect the word welcome, you need to see all the samples essentially with various location of welcome, which is not really scalable. Okay. So in this case, we will require a very large network, because the welcome word as such will be in a small window. But if you want to use MLP, then you have to feed in the whole thing in a big NLP, and that too in your training samples you should have many samples with the welcome at different locations. Okay. So that it will learn, right, whether the welcome is there or not. So this type of problem where you are looking for small piece, but it could be anywhere. Okay, you need to think. Okay, you need to use something else. Okay, not the usual MLP. So need a simple network that will fire regardless of the location of welcome. and not fire when there is none, right? So these are the motifs. So how many pictures below have flowers, right? So in this case, there are, I guess, 4 pictures with flowers. So this, this, and this. Okay. So will an MLP, multilayer perceptron, recognize the left image as a flower and also recognize the right one as a flower? Look, flower is a different location, right? So what is the guarantee that if you use multilayer perceptron and pass the whole image, it will recognize that both the images have flower? Unless your training data contains all these possible flower locations in the training data, it is not easy for MLP to locate the flower. Okay, so these are the issues when processing with images with MLP. Okay, so need a network that will fire regardless of the precise location of the target object. In many problems, location of the pattern is not important. Just the pattern is important, but where it is, it's not important. The conventional MLP are sensitive to location, and moving it just by one component, if your data shifts, then it won't recognize unless you have trained on such data. So we need a network that is shift invariant. So like this, we need an MLP that acts like a scanner. Okay, so it scans this small region, and then it scans the another small region, and so on until the end. So if this MLP is a good detector of the word welcome, okay, we will train that. Okay, we will train it to be like that with lot of label data. So if it becomes trained, then obviously it will scan once, and then it will tell you whether the word welcome it found somewhere or not. Now the word welcome could be anywhere, so it is kind of shift invariant now. Okay, rather than taking full MLP, now wherever it could be, this should be able to scan and find out. So this is how it might look like. Your MLP might scan through this. This is a 1D example, so you will scan through this with some shift. Okay, how many strides you take, it also you have to decide whether you skip 1 pixel or 2 pixel at a time, or in this case it's like the vector dimension, let's say. So this is how you are going to scan. So while scanning, each time your MLP will process and say, and it's kind of identifier of the word welcome, right? So it will say with how much probability in this area the word welcome is there. So it will produce some output with probability value, let's say, and then it goes to this window and say how much probability is there of the word welcome here, and will keep doing that, and it produce this, let's say, probability values, and then you can do a max of this, argmax or something like that, and then you will see, okay, maybe I mean, in this case, it's just not like where I want to find, that's not a problem. There was there or not, right? So in that case, you just say max, and then you say, okay, there was 90% probability that one of the reasons there was a word welcome. Okay, so this is what we need, and as you can see, we need something like this. So this is a very simple way to write a scanner, right, for a 1D scanner. So this is an MLP, but it is acting like a scanner. So this MLP can start from T is that like time steps it goes through windows. So let us say 1, 2, and if this window size is k by k, and then you will go up to T minus of k minus 1. So which is like T minus k plus 1. So basically you will move this many times, and each time you will pick a segment that starts from T and T plus k minus 1, because k by k window you are scanning. So from your current location you go up to T plus k minus 1. Okay, and that's the segment you will take out, and then you will pass it through MLP, and MLP will give you some output value, probability values of the word welcome. And this way this for loop works. So this T goes to the end, it has scanned all the segments, and then finally you do a max of this guy, and that tells you whether it's a welcome or not. Okay, so another way to view this is that you could have seen this as a giant MLP also, although it's a small MLP scanning through the region, but you could have kind of on another way to see is that there are so many copies of MLP, but they are the same, also they are copy, right? So another view is like you see them as a copy of so many MLPs. So scanning in 2D goes in a similar way. Now you have to go left, so you have height and width also. So there's some slight adjustment is needed, but there is an MLP that's scanning this area, and this is how it will look like. So it scans this area, then it moves right a little bit. So again, this is MLP is like a flower detector now. So it will say whether it found a flower here or not. What is the probability here? And then this window shifts, and here what is the probability that flower was there? Here what is the probability flower was there? So it goes right, and it also goes a little bit down. So basically it is supposed to scan the whole image. So this is how this works. So it is scanning through the window, and each time the same MLP is scanning this window, and then it went so after scanning this, it already produced an output that is saved. Okay, so it doesn't matter, this same MLP can be used in next time, and then it takes the input, processes, and it gives an output that is saved. So this way this scans everything, and finally we do the max. So in 2D also it's kind of similar. Now this is the algorithm to scan in 2D case. Now you have I and j index here. So you have the index to go in the x direction, let's say, in the width. So this is again a k by k patch, right? So you can go up to w minus k minus 1, and then j will go from h minus k minus 1 times, and then in this case you have to pick the 2D image segment. So from your current ith pixel, you go to I plus k minus 1 pixel, because that's the window size you are supposed to take out. And similarly for the j, you go from j to j plus k minus 1. So once you have extracted this index from the image, it goes into MLP, and this gets processed, and you save those, and then you again do the softmax to detect whether the flower was there or not. Okay, so these are the kind of things that you do as a scan. And if it was a full MLP, then this is how it looks like. All the weights kind of get full, right? If it was full MLP scanning the whole thing, then the number of parameters are drastic. But if it is a scanner, like in this case, is scanning like this, then the number of parameters in the network can be seen like this. But this block, as you can see, is the same MLP, so the weights here have been copied. So another view is that it could be seen as a big MLP scanning the whole region, just that it is the same MLP, so these weights are just copied on the diagonal. So this is how the scanning works, and how the weights are. So I guess we can stop here today, and we will try to complete the CNN in the next class, and also see some interesting applications in GAN.